So buoyancy force is the force that, if you're immersed inside of the fluid, the force pushing you up is the buoyancy force. Or if you're just partly in the fluid. So buoyancy. So real quick, we'll go through this derivation one more time, just because we rushed through it quickly last time. The way that this worked was if I imagined I had a container full of some fluid with some density rho. So here, density. Let's say I have a box in there, and that the area of the top of the box is A. The height of the box, say, is H. And we'll say it's a cubic box, so all the areas are the same, or at least rectangular. So top area and bottom area are the same. If I have this, what's the pressure at any depth inside the fluid? Do you remember the formula for pressure at a given depth?
P is density times G times depth.
Yeah, that's right. So it's rho times G times H, or times depth, D, sorry. Say this is the depth, D. Go on. That's the pressure plus whatever the atmospheric pressure is. Okay, that's our formula for pressure inside of a fluid. All right, and that just comes from looking at the total mass in the column of water above the object. All right, so pressure is force per area. It always exerts itself inwards on any object I place in there, directly inwards. So at the top surface of this, I have a pressure going here, and at the bottom surface, I have a pressure going directly towards the bottom. All right. The total force on this top surface, let's go ahead and see what that is. The force, I'm going to call this F1 on the top surface and F2 on the bottom surface. So what's the total magnitude of the force F1 on the top surface? Be the pressure on there times the area of that surface, wouldn't it? Because pressure is force per area.
Yeah.
So force 1 would be the pressure at point 1 times the area. And it would point in the positive y direction, wouldn't it, if I were to put a vector on this, here like this. I can substitute in what this P1 is. It would be rho v d A plus P atmosphere times A times y hat. See what I did? I just took this, multiplied it, just substituted it in there, multiplied through by A. Okay. Now let's look at force 2. That's the force on the bottom surface. This would, and this would be in the positive or negative y direction on the top surface. Maybe we ought to define a y direction first. Let's do it like that.
And
What's that?
negative?
Be negative, wouldn't it? So we're pushing it downwards, the pressure on the top surface. Okay, force 2, that's the force on the bottom surface. The magnitude of that would, it'd be P2 A y hat. Okay. Now, P2 is slightly different because instead of just being a depth D, it's a depth D plus H.
Do we also have to include PATM on the bottom?
Yeah, if we want to be consistent, you'll see that it all subtracts out. So this would be rho V D plus H, because now that's the depth. plus the atmosphere. Okay, so I'm going to substitute that into here. And I'll get rho G dA, just multiplying this out times A, plus rho G dH, or rho GHA, sorry, multiplying the rho GH times A, plus P atmosphere, A, whole thing, y hat. See what I did there? Now, if I'm interested in the total force on this object, or the buoyancy force on the object, I want to look at the sum of all the forces due to pressure. I'm not going to worry about the pressure on the sides, those cancel out. And from experience, we see that if I just put something, an object in a fluid, it doesn't just go sideways. So the forces along the sides always cancel out. Proving that's a little, we could go through it for a cubic box. So let's see what the total force due to all the pressures is. So I want to do, this will be the buoyancy force. So F1 plus F2. And when I do write that out, I would get, I'm just going to write it out in gory detail. F1 is minus rho GV minus dA minus P atmosphere A. And that'll be in the y hat direction. And then I'm going to, before I do that, before I write any y hats, I'm going to also include the next forces. F2 would be plus rho G dA plus rho G AH plus P atmosphere A, whole thing in the y hat direction. You see that? When I added up all those forces, these two were from force 1, the rest of it was from force 2. You see that this cancels with that, and this cancels with that. And I'm only left with rho G dA. Oh wait. No, this cancels with that. This doesn't cancel, does it? Sorry. I didn't recognize the difference between a D and an H. Rho H. Okay. So I'm left with rho G A H y hat. Now that area times H, what is that? So I look at this little box here, this area up here, times this height of the box, what is that? That's the volume of the box, isn't it? Mm-hmm. So this would be rho G V y hat. And that's the buoyancy force. So it points upwards, has a magnitude equal to this rho times V. This will be the volume, in general, turns out to be the volume of the water that's displaced by putting the object in the water. So if the object is completely submerged, that V would be the total volume of the object. If it's partly submerged, it's just the volume that's in the water, below water level. That makes sense? So V equals volume of water displaced or moved around. Displaced by object. Does that make sense? And then rho is the density of the object, of the water. And then G is cool. And so that's a buoyancy force. Now, if I want to have an object floating or something like that, that force should balance the gravity force of the object's floating. So let's go ahead and do some examples of this. Okay. First example. Let's say I have a box that has a height h and 2/3 of h is below the water level. And this is just floating here. Let's find the density of the box. That's the first question. All I can do this one. Do you want me to do this one, or do you want to give it a try?
Okay.
Thank you. All right. I'll do this one, and then I'll give you guys one, okay? All right. So first of all, I'm going to draw a free body diagram for that box. When I do that, and what are the forces on this box? We'll treat all the pressure forces as acting together in one buoyancy force. So so if I draw the free body diagram for the box, what are the forces? And G going downwards, good. Well, we're going to treat all of the pressure forces as together as just giving us the buoyancy.
So normal force? Would it have a
So
normal
then
force?
buoyancy going up.
So the normal force of the pressure is kind of the buoyancy force is kind of the normal force of this sense. Buoyancy force going upwards. If you notice, we took into account when we derived the atmospheric pressure, and it ends up canceling out. Okay.
That's it.
So that's it, right? So this mass of the object, let's call the density of the box, rho box, and the density of water, we'll just call rho. Let's introduce the top as having a cross section A. Okay? So, what's this M?
Mass of the object?
Yeah, what's that mass of the object in terms of density?
Density?
What's the relation between mass and density?
Kilograms
G.
per mass.
Density
No,
times volume.
I mean, per,
Density times volume, very good.
yeah.
So rho box times V of the box. Now I'm going to write V of the box, I'm just going to write it out. It's going to be A times H, right? Good. That's M. So I can write that the sum of forces in the y direction is going to be the buoyancy force. That was this here. So that's going to be density of water times G times the volume displaced by the water minus mg, which is rho box A H times G. And if it's floating, what should that be equal to? Is it accelerating? No.
0.
So it's just going to be MAY, which is 0 in this case. You see that?
Mm-hmm.
All right, what's this volume that's displaced by the volume of water that's displaced by this box when it's floating 2/3 H down? That would be this amount of water.
Two-thirds H.
Yeah,
times A.
2/3
Yeah.
cube.
That would be A times 2/3 H. Right? Let's go ahead and substitute that into here. And I get rho G 2/3 AH minus rho box AHG. Oh, there should be a G there. Is equal to 0. I can cancel out a G, divide both sides by a G, divide both sides by an A. That's why I didn't give you A, because just introduce it and it divides out. And I can divide through by H. I didn't have to tell you what H was. Oh, and that G should be gone, right? I can bring this rho box over the other side, and I can see that 2/3 rho, which is the density of water, is equal to rho box. And so that this was, how much is water, the density of water?
1,000 kilograms per meter cube.
Yep, very good. So this is 2/3 times 1,000 kilograms per meter cubed. That's 67 kilograms per meter cubed is rho box. Make sense? Yeah.
Where'd you get that second G by DH?
Oh. I shouldn't have put in both G's. Now I see where I made a mistake. Okay. Thank you, Byron. That's a good, it's a good catch. You guys follow? All right, you ready for another one?
Wait, what is it? 667 kilograms per meter square cube.
All right, now I have a triangular cross-section ship. Triangular cross-section ship. So if I look at the ship, it has a length like this. And if I look at it, this means an observer. It's supposed to be like an eyeball. If I look at it from the side, the ship looks like this, okay? And the total height of it is height H. Okay. So, I want this distance to be 10 meters, and I want this distance to be 10 meters. Okay? L is 200 meters. Long ship, but not that, not unreasonable. Okay, what is the mass of a boat? Oh, yeah, probably, yeah. Sorry about that. This is also, this is 20 meters. Okay. So, anyone know what the Panmax ship width is? For a long time, a lot of ships were designed so that they had the Panmax size. That's a maximum width of ship that could fit through the Panama Canal. Anyone know what that is? Alright. I don't know. What's that? Yeah, they changed it. And that's why they can have bigger ships now. They also, I think they tested the Suez, which is the busiest canal. So that they can have some bigger ones.
What is that picture drawing? Like, can you explain that?
So that's the length of the ship, right?
Oh.
So, all right, let me see if I can draw it. So, this is, I can't draw a ship. So my ship is very simplistically. Kind of a wedge like that, okay?
So it's like a triangular prism.
Triangular prism, perfect. Yeah. Make sense? So length 200 meters, width 20 meters. You want 10 meters of it to be below the water and 10 meters above. That's the maximum weight of the ship. So I'll give you guys 3 or 4 minutes to work on this. Work with the person next to you, okay? We can assume that we'll assume that it's water. Salt water is like 1,025 kilograms per meter cubed as opposed to 1,000. So there's a little difference, but it's not huge.
So the area is getting the top of the ship.
This triangle here.
Yeah, that's what I wanted.
Similar size. It's just one half the size.
After the column.
Okay, here we go. So, it's halfway there. So is that a quarter? The volume is 1/4.
That's times
Area.
volume.
This is,
Yeah, so that's what
there's 4 triangles.
And then leave it like that. Exactly.
Because
That's
this
what
is exactly 1/2.
So we're gonna learn to move to the area. Then we got, that's the only,
So the amount that's underwater is 1/4.
This is it.
I don't know.
Yeah, I know.
This is
Don't-
volume.
Yeah, this is volume, but, yeah, I know this is volume. If you don't, for air, how how
A
how
quarter of the So, yeah.
yeah, what like no, he just hinted that
That makes sense.
oh, for the water. For the water. One half of the
Or you should actually you like to figure out how it's actually
one half split.
It's just one half.
So
The area under is 1/4. Because like,
where are we at one?
right?
How do you know?
What's that?
I just included Bradley.
What about the triangle? What's the volume of the triangle? It's
Yeah.
So did you get the bottom half of it? Oh, okay. Count at all.
Okay, you ready? Anyone have an answer? Nobody has an answer. I like the 10,000 metric tons. Did everyone get that? Everyone's out of now. Nobody got it, huh?
No, I didn't get that. I got 1,000.
Okay, 1,000. Anyone else got anything, or you just completely clueless? On this problem, just on this problem. All right. All right, we'll go ahead and do that. So there's a couple of things you could do. We'll start out.
Okay.
If you really want to and do a lot of work, you could say, okay, if I cut this triangle in half, this would be 2 right triangles. I can figure out the angle of this, knowing that this is 20 meters and this is 10 meters. All right, and then I could then figure out how far that is, knowing that angle's, knowing this angle, and then this being 10 meters, I can figure out this angle. That's one way to do this. Another way is to notice that if I take this triangle, and if I just look at the part of the that's submerged, that all the angles in this little red triangle are the same as all the angles in this big triangle. That means there's something that that the big triangle and this red triangle are similar triangles. What that means is that the ratios of all lengths, corresponding lengths in those 2 triangles are the same. You guys ever heard of it? You guys ever seen that with similar triangles?
Yeah.
Geometry.
All right, yeah, it's geometry. If you don't remember it, you can do it the trigonometry way. Just this more work. So if this is 20 meters, and this is 20 meters, and then this is 10 meters, that means this has to be 10 meters. So that top thing is across, right there, okay? So, we want to figure out the total volume of water that's displaced, because we know that the buoyancy force is this, which is density of water, V times the volume of water that's displaced. So V is going to be the area of this triangle times the length, right?
So 1/2 length times width.
Yeah, so the area of the triangle is 1/2 times 10 meters times the length times the width. 1/2 times this 10 meters times that 10 meters high. Times 100 squared. That's the area of the triangle here. And then I multiply that by the total length of the ship. Okay. And that 2 can cancel that 2. Left to go 1. So this would be 10 to the 4th, or 10,000 meters cubed. All right, if I drew a free body diagram for the ship, draw a little box for it. I have the buoyancy force upwards and mg downwards. In equilibrium, these two things are equal. The buoyancy force, the magnitude of it, is rho times the volume of the water that's displaced times g.
Equals them.
And then this is just the mass of the water that's displaced, right? The density of water times the volume of the water that's displaced would just be the mass of water that's displaced.
Uh-huh.
So mass of the, so if I look at the sum up the forces in the y direction, I'd get the buoyancy force m water times g minus mg is equal to 0. Or that the mass of the water that's displaced would be equal to m. So for instance, when they're talking about mass of a ship, they often talk about the ship displaces this many tons of water. And that's how they measure the mass of a ship. Okay, so that's something that that's the mass of the water that's displaced will be equal to the mass of the ship when it's floating there. All right, so this is the mass. Rho volume will be mass of the water. The volume was 10,000 cubic meters. What's rho for water?
1,000 kilograms.
Yeah, so rho is 1,000 kilograms per meter cubed. So this would be 10 million kilograms, so 10 to the 7 kilograms. Mass of water, which is the mass of the ship, is 10 million kilograms, or 10,000 metric tons. It's actually not that big of a ship. Anyone know how big some of those big oil tankers get? I think the biggest one ever was, of the oil tankers, was 500,000 metric tons when it was fully loaded, or tons when it was fully loaded. Good? All right, buoyancy.
So rho times the volume equals the mass of the water.
Yeah. Rho, the density of water times the volume of water that's displaced would equal the mass of the water that's displaced.
Okay, and the volumes that's displaced is just that one triangle.
Yeah, the volume displaced is the amount below the water. Okay?
So we didn't even need to swap the volume of the water displaced, did we?
You
Yeah,
did
we
need
did.
the volume.
Oh.
Because you have to multiply that by the row to get there.
Yeah. All right. So that's buoyancy force. That makes sense to you guys? All right, one more thing that we'll do with it.
In this case, we basically deal with, we don't care if we get talking about this 500 million displaced. Talk about it.
Yeah. Okay. So, let's consider a pipe. it's sloping upwards, then maybe it's a little bit less than so. There's water flowing in it. Let me see if I can get some. The water will be green. Okay, let's say I have a pipe looking upwards, water in it. Say that there's some angle that it's at, so that this distance from the beginning, this distance, the height is h, the height that it rises. All right, let's consider the column of water in this. And say that the pressure on this end is P1, the pressure on this end is P2. We're going to go ahead and derive something, and the derivation is a little bit slightly sketchy, but it's not too bad. This will assume we're dealing with something called an ideal fluid. Ideal fluid means that if I start mixing it, and that energy doesn't get lost, which is not very realistic at all. Real fluids, and also that it flows without resistance at the same speed throughout the cross section of the pipe. And real fluids, if I look very closely at the edge of the pipe, the fluid is not moving there. And if I go towards the center of the pipe, it goes faster and faster. That's due to what's called viscosity, or the tendency of the fluid to kind of stick on the sides. Those are real fluids. We're not going to deal with those. We're dealing with a very idealistic fluid. Okay? And we're assuming it's incompressible, so it's a liquid. Idealistic. This idealistic means it all just flows at once happily. All right, let's say that this has a cross-sectional area, A. So that if I looked at the edge of the pipe, I'd see a circle or whatever the shape of the pipe was, and and that area is A. And let's call this total length of pipe L. Okay? What I want to do is I want to look at the work done by the pressures as this fluid moves upwards. Okay? And also the work done by gravity as this fluid moves upwards. Okay. So, here's what we're going to assume. As this whole column of water moves up to here, we're going to assume that always on this side of the column, the pressure is P1. So the force here would be, magnitude of force would be P1A. And that points in this direction straight up along the pipe. Force on this end is that way, force 2. We're going to say that the magnitude of force 2 is P2A. Okay. So the total work done by pressures, work total, is going to be the work done by the pressures on the edge of the fluid, which the work due to P1 plus work due to P2. And then since it's in principle also going uphill, there's also work done by gravity. All right, now, what do we know about the total work on an object? What's that work kinetic energy theorem? We found out that, we realized that if that the total work is equal to the change
And kinetic energy.
Yeah, that's right. Thank you, Salome. Change in kinetic energy. Everyone get that? All right. So, let's say this is moving with a speed v, v1 here. And up here, let's say the column is moving with a speed v2. Sorry, this is getting complicated and messy. So the change in kinetic energy as this whole column of water moves upwards would be 1/2 mass of the water, v2 squared, final velocity squared, minus 1/2 mass of the water, v1 squared. Final minus initial kinetic energy. The mass of the water, it says the density rho. The mass of the water is the density of water times the volume. So it would be rho times the volume, which would be area, cross-sectional area times L. Minus 1/2. Do you see how I got that? Now let's go ahead and see what all these works are. This is equal. Work kinetic energy theorem says that has to equal the total amount of work done. Okay, the work done by pressure 1, that'd be the force 1 times the distance moved in the direction of the force. So what would that be? What's the force?
P1, A1.
P1, A. And then how far did it move in the direction of the force?
Oh, cos.
Just L, right?
Oh,
Because it's moving along the pipe. Is that good? Work done by pressure 2. What would that be?
P2A.
L cosine of
Cosine
180
of-
degrees now, so that'd be negative. Because that force is going the opposite direction of the movement. Work done by gravity is just negative the change in potential energy. That would be minus mgh. And that would be minus rho ALGH. All right, let's write out all of this combined together and then see what we get. So we will get 1/2 rho AL V2 squared minus 1/2 rho AL V1 squared is equal to P1 AL minus P2 AL minus rho AL GH.
I got a tap in here.
Broke science.
Oh, that's funny.
Notice here that everything has an A and an L in it, doesn't it? Area and the length of the pipe. So I could divide the whole equation by that. AL. Like that, right?
What was L again?
Length of the pipe, length of the column of fluid. Okay. So I get 1/2 rho V2 squared minus 1/2 rho V1 squared is equal to P1 minus P2 minus rho VH. Now I'm going to introduce something. I'm going to say that the height of the pipe here is H2, and the height of the H here is H1, so that the H is H2 minus H1. Okay? Driving one. In that case, I can write this as H2 minus H1. All right, ugly looking thing, a lot of derivation. I'm going to put everything with V2 on this side, or with a 2 on this side. Anything with a 2 corresponds to this end. I'm going to put everything involving 1 on the other side of the equation. 1 corresponds to this end of the pipe. And what I end up with is, okay, so I get 1/2 rho V2 squared. This P2 I'm going to